So, we saw that the intensity of the vibrational core structure varies. Okay. The spectral lines that forms the core structure of electronic spectra, that is basically coarse vibrational structures, and why the intensity varies, that we have seen from Franck-Condon principle. Now, so we have this now vibrational spectra, okay, electronic spectra, but that core structure of this electronic spectra is basically vibrational core structure. And now, what is the use of this core structure? What information we can get from this vibrational core structure? So, that I want to discuss. So, so we have seen that this here you can see basically dissociation energy and dissociation product. So, as you know that these molecules are vibrating, so they have different vibrational energy levels, right. Now, here and this vibration is basically asymmetric, which follows this Morse potential curve, and here you see this separation when it is going higher states, and its separation, this internuclear distance are increasing, okay, and ultimately at this level it will, this atoms will be dissociated, these molecules will be dissociated, and this it will basically this, it will not be no longer molecules. So, this molecule will break and we will get this product, it is called dissociation product, that basically the individual atom will get. So, molecule, diatomic molecule, 2 atoms was there. Now, at higher vibrational state, if it is higher vibrational level, so at a particular value of vibrational quantum number, higher value of vibrational quantum number. So, these molecules will dissociate, and this will get the dissociation product, that is nothing but the in form of atoms. Okay. So, how much energy required to dissociate the molecules, to break the molecules? So, that is the basically dissociation energy, and what will be the energy of the product, dissociation product. Okay. So, this here, so here again this is the one electronic state, and this is the another electronic state, okay. And in each electronic state there are vibrational levels, okay. So, when these molecules in this electronic state, and it has different vibrational level. So, if in this level, in this electronic states itself, if these molecules dissociate, then the amount of energy, it is d0 double dash, okay, is required to dissociate, to break the molecule. So, this energy is called the dissociation energy for this say ground state. Okay. Now, when it is excited state, excited electronic state, and in excited electronic state there are vibrational states. Now, molecule is in a electronic excited state. Okay. Now, in this electronic excited state, if molecules dissociate, if molecule breaks, okay. So, what is the dissociation energy for this? Yes, for this excited electronic state. So, this basically here d0 dash, okay. So, this much energy required to breaks the molecules when molecules is in the electronic excited state. Okay. Now, molecule is in this ground state, ground electronic state. Okay. Now, it is excited, the molecule is excited in the higher electronic state, and then it breaks, also dissociate. Okay. So, that means say that in this electronic state this molecules was in this vibrational level, lowest energy vibrational level. Okay. Now, in this condition if it dissociate, so now ultimately it will go to electronic state and then highest vibrational state where it will breaks. Okay. So, then one need basically this much energy to dissociate the molecules. Okay. So, so here this d0 dash and d0 double dash, this is the dissociation energy, and this energy is only when it is already in that electronic state, either in this ground state or in this excited state. Now, after that if you want to dissociate either in this state or in this state, so these are the dissociation energy. But another case, this electronic transition as well as this vibrational transition both together. So, from this state to it is coming here. Okay. So, that means it will dissociate in the excited state, in the excited electronic state, coming from the ground state, ground electronic state as well as ground vibrational state. So, then this will be the total energy required to dissociate the molecules. So, what will be the energy? What will be the energy of the dissociation product of the that dissociation product that basically atoms. So, here basically here in this case if d0 dash or double dash is the dissociation product is basically in both cases it is atoms, but the energy in this case as I mentioned that from this electronic energy state to the next higher electronic state as well as the vibrational change. So, in that case the total energy basically it is the energy difference between the product, energy difference between the dissociation product. So, that means the energy difference will be this one. Okay. So, if in this case if it is dissociate, so the energy of the product will be d0 double dash, and another case it is dissociate in this way. Okay. So, energy will be this. Okay. So, that is the energy of the dissociation product. So, what will be the energy difference between these two? So, that is basically one can write here. So, from here, so this is called the excited energy Ex I have written. So, from here one can write that d0 double dash plus E excited. So, basically that is this. So, d0 double dash plus E excited. Okay. So, that will be the energy of these spectral lines or wave number of the spectral lines. Okay. And that's the it's called continuum limit. because here from this transition you can see that is the basically at the continuous this continuum level of the spectral lines. So, this one can tell this nu var continuum limit equal to basically nothing but this dissociation energy d 0 double dash plus this E excited. Okay. So, so studying the this basically this from the spectroscopy measurement one can measure this wave number of the spectral lines and determine the dissociation energy. So, that I will discuss. So, how spectroscopy is used to determine the dissociation energy of the molecules as well as the other parameters like anharmonicity constant as well as this say omega E bar. So, this natural frequency of the oscillator. So, that we will see. So, that is basically that people use the absorption spectroscopy. Okay. So, what is absorption spectroscopy? So, spectrometer, you know this spectrometer. So, it has collimator, it has this table, prism table, okay, or grating table, and then we have the telescope. Okay. So, collimator is so basically here generally people use the grating because grating has higher resolution power. Okay. So, so spectrometer basically contain the three component. One is collimator, another is table where we put the prism or the grating, and you have option to rotate and measure the angle, as well as we next component is the telescope. So, so basically this collimator, in collimator there is a prism, there is a lens, convex lens, and this makes this basically this lens is used to make the parallel rays, okay, to fulfill the condition of Fraunhofer diffraction. Okay. So, so from source at a finite distance, light are coming. Now, they are basically these lines are diverging line, light diverging lines, okay, rays. Now, if it falls on the lens, means it is passing through the collimator, falling on the lens. Now, one can change the distance of the lens, so that the source can be at the focal point of this lens. So, source is at the focal point of a lens, then other side you will get the parallel rays, as if the source is at infinite distance. So, source is at infinite distance, then the rays comes, then that we tell that it is a parallel rays. So, in laboratory, so this the way we get the parallel rays, as if light are coming from the infinity. Okay. Similarly, collimator this side, another side is telescope. In telescope also there is a lens. So, that also in Fraunhofer diffraction image also formed at the infinity, but again using the lens. So, this lens again we change the position in such a way that the screen here basically eyepiece, screen at the screen will be at the focal point of the lens. Okay. So, we will basically the image will form on this eyepiece or screen, which should be at the basically infinite distance, because parallel rays will form the image. So, it is only possible parallel rays will meet and form the image at the infinity, but using the lens that in laboratory that we fulfill the Fraunhofer condition and get the things at a finite distance. Okay. So, this the I think this is the spectroscope, the spectrometer, that is the general configuration of any spectrometer. Now, the spectrometer is used for this for the determination of the vibrational frequency, anomalistic constant, as well as dissociation energy of molecules. So, this spectroscopy here, different kind of spectroscopy is there. So, here whatever I am discussing now, that is called absorption spectroscopy. Okay. So, what is that? So, think that there is a source of light, source of white light, means all sorts of wavelengths are available in this light. So, now if this light if you put in the grating spectrometer, okay, if you use grating spectrometer, so what you will get? You will see the diffraction. Okay, you know diffraction d sin theta equal to n lambda. Okay, so wavelength is higher, so it will be deviated. It will be deviated more from the direct light. So it will be deviated more. So this at higher angle you will get the red light. Okay, and lower angle you will get the other light, green light, say. Okay. So, you will get basically the here you will get the spectra of different color, and it is you will not get basically lines, because all wavelengths are available. So, only you will get the distribution of color, means whole space will be illuminated, but only colors are separated. Okay. So, this type of things you will get. Okay. So, now if I put say some gas in a cylinder, okay, cylindrical tube, if we put gas and then this white light is coming now, this light is passing through this gas. Say here I have taken iodine gas. Now then through the gas this light is coming out. Now again this light is analyzed using the grating spectrometer. Now what we will see? So without gas this type of distribution of the color was observed. Now if you put gas, so you will get basically this type of distribution of the black lines. Okay. So that means you will see the black lines in this bright distribution of the colors. So there basically you will see the many black lines, and black lines are arranged like this. Okay. So this side, one side is the order. Okay. So this is the basically n equal to so 0. Now this side n equal to 1, this other side n equal to -1, etc., etc. Okay. So so basically here basically the black lines you are getting. So that we are telling these wavelengths are absorbed by this iodine gas. So that is why this is called basically absorption spectroscopy. Okay. So so absorption spectroscopy basically we will see the lines, black lines, that corresponds to the absorption of that wavelength, and in this absorption spectroscopy in case of iodine gas, so this type of spectra, absorption spectra is observed. This type of absorption spectra is observed. So, here you can see this. These are the lines. So, these lines are V equal to 0, V equal to 1, V equal to 3, 2, 3, 4, 5, etc. Now, it is one can understand easily because this absorption spectral lines is basically correspond to the vibrational. It tells about the vibrational energy levels in this iodine molecule. So, this type of spectra you will get now measuring this wavelength, measuring this wave number for different vibrational quantum number. So, that is possible in this using the spectrometer. So, that is the spectrometer. One can find out the wavelength of the spectral lines or wave number of the spectral lines. Okay. So, this type of spectral lines will be observed, and this is nothing but the vibrational core structure. Okay. Vibrational core structure, and now measuring the wavelength or wave number of the spectral lines, one can determine these parameters whatever here I have shown, that vibrational frequency, then anharmonicity constant, and dissociation energy of the molecules. Okay. So, how it is done, that I will discuss. So, that also very interesting. So there is a so that spectral lines we are getting, that is basically it's the yeah. So, that's the energy of the spectral lines in centimeter inverse, of course, right. So, now what is the separation? What is the separation between the two spectral lines? So, if that is del E, so this separation is the spectral lines is basically progression type. So, E V plus 1 minus E V. Okay. So, if you do that, so you will get this. Okay. So, separation of the successive spectral lines, so that separation, that wave number is del E, and that is this. Okay. So, from here one can see that separation will decrease, because this is minus is there, 1 minus this will decrease for increasing vibrational quantum number. So, vibrational quantum number V will increase, separation of the spectral lines will decrease. So, del E decrease with increasing V. Now, from vibrational absorption spectra, that is what we have seen. Now, one can measure del E for different V, right. So, the spectral lines are there. So, one can measure the separation between two successive spectral lines, and that is basically for different value of V. Now, if you plot this separation, if you plot this del E versus this V, so you will see that with higher V, so it will, this separation is decreasing, Okay. Now, here I have connected them, it's with straight line. It is actually, it is not exactly straight line, but here formula whatever we have taken, it's here it is telling straight line, but if you consider the higher terms that we have neglected, so it is not exactly straight line, but one can approximately consider it as a straight line. So, I have connected them with dotted line and extrapolated in both sides, because it is very difficult to identify the spectral lines, whether it is which one is V equal to 1, and what is the, and at the continuum limit what is the value of V. So, that is difficult to identify, but using this plot if we extrapolate, so one can find out the V max, this continuum limit. So, how one can find out? So, here del E is at this point del E equal to 0. So, del E equal to 0 means this part, this is equal to 0. Okay. So, then you will get basically V max equal to 1 by 2 x e minus 1. Okay. So, from here basically one can get experimentally one can get the value of V max. Now, putting the using this V max, okay, here one can find out the anharmonicity constant of the molecule. Okay. So, this is very interesting. So, this way one can determine the anharmonicity constant. Similarly, one can find out the dissociation energy. So, D0 dash or D0 double dash one can find out. So, D0 dash. So, here I have written that area of the plot will be equal to D0 dash. How? So, what we have plotted here? We have plotted here basically the separation of the spectral lines. So, separation of the spectral lines is nothing but the separation of the vibration energy levels. Okay, because we are considering just successive spectral lines. So, basically here whatever we have plotted, so that is that's the different energy difference between the two levels, successive two levels. So, here we have plotted here basically this one is this. So, the next one is this. So, next one is this. So, their separation is decreasing. So, that is why it is decreasing and goes to 0. Okay. Now, if I take the area means I am adding all the separation, I am adding all the separation basically, right. I am adding all the separation. So, add means is I am adding this one with the next one, then next one. So, I am basically here after adding I am getting the energy from difference from here to here continuum, So, this is nothing but the D0 dash. Okay. So, that is why here I have written the area of the plot. So, you plot it, extrapolate it and then find out the area of this plot, and then that is nothing but the D0 dash. D0 double dash as I have shown there, so that is basically energy of the 0 state, energy of the 0 state, this one energy of this plus D0 dash, okay. So, from here to here and then D0 dash, okay. So, plus D0 double dash, that will be basically the E excited. No, I think this plus D0 dash. So, that is the that will be equal to the D0 double dash plus E excited. So, that is what I was showing you. Yeah, I think this the D0 double dash plus E excited, okay. That is equal to V continuum. So, V continuum comes from the basically that is the this to this plus this D0 dash, okay. So, that is means this total is basically this 0 energy between the energy of this 0 spectral lines plus this D0 dash. So, that is the total that energy. So, that will be equal to the D0 double dash plus this E excited. So, that is why I have written here. So, how to get D0 double dash? So, this is the energy of 0 plus D0 dash plus minus Ex centimeter inverse. Now, D0 dash I know, energy of the 0 also you will know, you know, okay. So, because basically separation you are measuring means you know the wave number of each spectral line. So, 0 0 lines you will get yes, and only this E excited, that is not unknown, that is unknown, and this E excited is this nothing but it is related with the energy of the product, you know, because that separation is the here you can see this energy between. So, this is basically this energy of the dissociation product in this state, and this will be the this d0 double dash plus this okay. So, that will be the energy, I think here that is what we have written. So, dissociation product in this case is so this here whatever the product I will get. So, here dissociation product atoms, here dissociation product atoms. So, now different energy difference of this energy difference of the dissociation product in this case and this other case, they are basically atoms, and their energy difference will be this E excited one. So, basically this E excited one has to find out from the atomic spectroscopy, that one has to know. So, that is I think from atomic spectroscopy, that is easy, that is people generally find out this E excited. So, now that E excited one has to use and then one can get this D 0 double dash. Okay. So, absorption spectroscopy is frequently used in the laboratory. In fact, in our laboratory we use also this for this experiment, where student generally plot this daily versus V, and that is called basically Birge-Sponer plot. Birge-Sponer's plot, this very famous plot, and from this plot one can find out the this anharmonic constant. One can find out obviously omega E, one can find out because you are measuring the wave the spectral lines, wave number of the spectral lines. One can find out this this one also, this what is called this this frequency, fundamental frequency one can find out, as well as the dissociation energy one can find out. Okay. So, I think I will stop here. Thank you.